This is the topic of time scaling, a very important operation that we perform on sequences. Okay. And this is usually comes in the context when you are changing the sampling rate of a discrete time sequence. But again, we will talk about the change of sampling rate when we talk about sampling, but for now let us capture it in the following form. Let me give you a sequence. This is a sequence x of n, which is many zeros, and then finally starts with a 1, 2, 3, 4, 5, and then 4, 3, 2, 1, and then zeros. Okay. This is a finite length sequence. Is it causal? You say, okay, where is the origin? I didn't show you the origin. Okay, the origin is here. So finite length sequence, it is causal, and it starts with a sample value equal to 1. Okay, so let's sketch it for us here. Okay, so we have this particular sequence. It starts at n equal to 1, then n equal to 2, 3, 4, and 5, and then it comes down to 4, 3, 2, and then 1. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. These are non-zero samples. After that, it is 0. And the heights we can indicate as 1, 2, 3, 4, 5, 4, 3, 2, 1. Okay, so you are comfortable with this. Now, the first operation of time scaling is a reduction in the sampling rate. So, what we are going to say is, I am going to define a sequence y of n that is equal to x of 2n. Okay. So, which means that y of 0 will be x of 0, y of 1 will be equal to x of 2. Y of 2 will be equal to x of 4. So, just write down a few of those. So, y of 0 will be x of 0. Okay. Y of 1 will be x of 2, and y of 2 will be equal to x of 4, and so on. Okay. So, what does this sequence look like? So, basically we will take this same sequence and paste it over here with a different color. Let's say we'll make it blue, and what we have done is we have erased some of the samples. Okay, and we have now renumbered them as this is 1, 2, 3, 4. Okay, or maybe it's easier if you can look at it as a sequence. Okay, so y of n. So y of n is x of 2n. Y of 0 is the same. This sample got dropped. Next sample got dropped. This sample got dropped. This got dropped, and zeros of course are there. Okay. So 1, 3, 5, 3, 1. That is the new sequence that is obtained by this process. Okay. This process is basically we are doing a scaling of time. This is a process that we call as downsampling or compression. So, if you in general, if you write down an expression y of n is equal to x of mn, where m is an integer. Okay, and integer value meaning something greater than 1, 2n or 3, m is equal to 2, 3, 4 and so on. You are basically going to be doing a compression. So, this is a operation on time scaling which is called as compression or as downsampling. Okay, I like the term downsampling much better than compression. because it's very easy to see that you originally had 8 non-zero samples, now it went down to 5 because some non-zero samples got got omitted. Okay. Now, if I were to ask you to write down y1 of n is equal to x of 3n, okay, this would be a sequence, lots of zeros. You'll start with 1. Next sequence, next sample that will be present in your sequence, you're going to throw out 2 samples and retain the next one. So 2 and 3 got dropped, 4 will be the next sample. Then 5 and 4 got dropped, 3 will be the next non-zero sample, and then 2 and 1, and then zeros everywhere. So this would be the sequence that you would get for x of 3n. A fewer number of non-zero samples, and that's because you're doing the downsampling operation. Okay, so anytime we do a downsampling operation, there must be a counterpart, and yes, there is an upsampling operation as well, or a expansion operation, basically. So, before I forget, this has got a notation. We say that you take x of n, pass it through a downsampler marked by a down arrow and the factor m, and then this output is y of n, which is equal to x of mn. Okay, that's the downsampling operation. Now, moving on to the expansion operation or the upsampling. Expansion or upsampling. Very, very simple. What we are doing here is taking the samples that we already have and are going to insert zeros. Now, the question is, how many zeros are we to insert? So, here is we'll start with an example like always. So, if y of n, I want to upsample by a factor of 2. Upsample by a factor of 2. So, its input arrow now goes up with a factor 2. Okay. So, the definition of this is equal to x of n by 2 if n equal to 0, plus minus 2, plus minus 4, and so on. Because remember, a discrete time sequence is defined only when the argument is an integer. So, for all these values you will get an integer, and it is equal to 0 otherwise. Is equal to 0 otherwise. Okay. So, what is the, so y of 0 will be the same as x of 0. Y of 1, you will get x of 1 by 2, that's not allowed. So, therefore, that sample will be equal to 0. Y of 2, yes, that's an integer, you will get equal to x of 1. Y of 3 is 0, y of 4 equal to 2. Now, you know the trend, x of 2, and you can do the same thing for all the samples. So, the original sequence that we had, x of n, had many zeros and then started out with a sample 1, 2, 3, 4, 5, 4, 3, 2, 1, and then zeros. Okay. So, write down y of n. This sample was there, y of 0 is same as x of 0, by the way, this is the origin. Okay. And then the next sample of y of n was a 0. Then you had the value equal to 2, 0, 3, 0, 4, 0, 5, 0, 4, 0, 3, 0, 2, and 0, 1, and then all zeros. So, basically put a comma in between. So, you have inserted 1 0 between every 2 set of samples. Okay. Now, the general case of expansion, y of n equal to x of n by an integer n, uppercase n. Okay, x of n divided by n if n is a multiple of, if n by n is an integer. This will be true if n is equal to 0, plus minus n, plus minus 2n, and so on. And notice that for all other values, it will be 0. Okay. So, for n equal to 0, you will get a non-zero value. N equal to 1, 2, 3, you are going to get 0 values. And then eventually at n equal to n, you will get a non-zero value. So, how many zeros did you insert? N minus 1 zeros. So, this is a insertion of, basically this operation will involve insertion of n minus 1 zeros between every pair of samples. Between every pair of samples. Okay. So, if I were to say give me x of n by 3, not a problem, y or y1 of n is equal to x of n by 3 if n equal to 0, plus minus 3, plus minus 6, and so on, 0 otherwise. That is the exact expression there, the mathematical expression. You can also write down the sequence y1 of n. It will have the sample equal to 1, then there will be a 0, another 0, and then 2, 0, 0, 3, and so on this side, all the zeros. Okay, so and the origin will be the same point. Okay, the origin always is here, because origin does not shift. You start with n equal to 0, then from there on, the number of zeros you insert is equal to n minus 1. Okay, in this case n is equal to 3, I am inserting 2 zeros between every pair of samples. All right. So, now comes the our ability to combine all the operations that we have studied, and this is a very useful example and an exercise. So, let us look at an example which will combine all of the tools that we have developed so far in terms of operations on the sequence. Okay. So, I am going to define a finite length sequence which is given by 1, 2, 3, 4, 5, and 6. Okay, the origin is at 3. So, it is a finite length sequence. It is non-causal because it has got both sides, and this is a finite length sequence that we are going to be working with. So, I am going to ask you to do 5 different calculations as part of it. Some of them are easier, some of them would require a little bit of effort. We will go through them in a systematic way. The first operation is a shifting operation, x of n minus 3. Okay, which means that you have to shift the sequence. This is a delay operation. You are shifting the sequence to the right. So, the answer is going to be 0, 1, 2, 3, 4, 5, 6, and the origin moved to this point. Okay, moved 1, 2, and a third, and anything we are basically assuming it's a finite length sequence. It is zeros outside of this window. So, therefore, you can always introduce 0 valued samples. Second, y2 of n is equal to x of minus n, time reversal. So, this is a sequence which is obtained as 6, 5, 4, 3, 2, 1, and then zeros, the origin staying exactly where it was originally. So, 3 remains with it and the sequence flips around. Okay, now come the more interesting cases. y3 of n is equal to x of minus n plus 1. Okay, there are 2 operations, remember, it's a compound operation. There is a shift operation, there is also a time reversal operation. So, here is just a sort of a guide for you to do. So, the sequence in which, when you have compound operations, the sequence in which you should do first is the shift. Always do the shift first and then do the time reversal. Okay, if you have only these 2 operations, the sequence should always be in this order. It just helps you to do that. So let us do that. I am going to define a intermediate sequence y prime of n which is equal to x of n plus 1. Okay, only the shift part, the shift is plus 1, I am going to introduce the shift of plus 1. Okay, shift of plus 1 means it is an advance operation, the sequence moved to the left and your origin now shifted. So you have 1, 2, 3, 4, 5 and 6. Where did the origin move to? It was originally at 3. You advance the sequence by 1. So therefore, the origin now moved to 4. Okay, this is y prime of n. We have already done the shift. Now do the time reversal. So therefore, y3 of n is equal to y prime of minus n. What is y prime of minus n? What is the expression for y prime? Y prime of n is x of n plus 1. Wherever there is n, you are going to replace it with minus n. So therefore, this is the same as x of minus n plus 1. That is the expression that we want. So what did we do in the first step? We shifted it first. Then we did the time reversal. Now, if you do it in the order, you can do it in the other order, but invariably you will end up in confusion saying, do I have to advance or do I have to delay it? This is very clear. Plus 1 means a delay. Once the delay is done, you do the time reversal. Now, doing the time reversal, what is y? So this is y3 of n. For y3 of n, don't go back to x of n, go to the sequence y prime and do the time reversal. The time reversal of this sequence will be 6, 5, 4, 6, 5, 4, 3, 2, 1. 4 is your origin, right? 4 is your origin. This is the answer for y3 of n. So basically, this is the expression that we want. So what did we do? We advanced by one unit of time and then did the time reversal so that we get the correct expression for what we have. Let us try one more. I think it is important that we get this very, very clearly without any confusion. y4 of n is equal to x of minus n minus 2. Okay. What are the two operations? There is a time shift, there is a time reversal. What is the sequence we should do? Shift first, time reversal next. So let us do the same thing. Define y prime of n is equal to x of n minus 2. n minus 2 is a delay. So therefore, the sequence that we are dealing with now is 1, 2, 3, 4, 5, 6 and the origin now was originally at 3, has moved 2 units to the left and it is now sitting at 1. And y4 of n, we will write it as y prime of minus n. Y prime of n is x of n minus 2. So any value of n, you take it and you substitute x of n in that. So y prime of minus n is the same as x of minus n minus 2. So substitute, you will get x of minus n minus 2. That means time reversal of y prime of n is the sequence that we are interested in, and time reversal of the sequence that we are interested in is 6, 5, 4, 3, 2, 1. The origin is at 1. Okay. I hope you are comfortable with this. This is a important and useful tool for us. All right. Now comes a final operation, which is a complex compound operation, where you have y5 of n is equal to x of 3n minus 1. Okay. What are the operations involved here? There is a shift operation. There is also a time scaling operation. Okay, very, very important to recognize that. So what is the shift operation? Shift by 1. So remember, we will. So previously we said shift and then time reversal. Okay. Now you can also say, okay, now this time there is no time reversal, but there is a time scaling. This is a good way of looking at the sequence in which you should do the operations even in the context of. You can also do equally easily. If all three are present, then you can do shift, you can do time scaling and time reversal. Both these sequences are fine, but always do the shift first. That's an important step. So time reversal. Okay, we will, in this case there is no time reversal, only time scaling is there, so we will take a look at that. So intermediate sequence, y prime of n is a shifted version, x of n minus 1. You know how to do that. It's a sequence which is shifted to the right, delayed by 1 unit of time. 1, 2, 3, 4, 5 and 6. The origin now is at 2. Okay. The time scaled version, y5 of n is equal to y prime of 3n. This is the same as, we substitute y prime of 3n is the same as x of 3n. Wherever there is n, you substitute 3n minus 1. That's the expression that we want. So what you're going to do is, you're going to do a time scaling operation on this sequence, y prime of n. 2 will be retained, right? That's corresponding to index 0. The sample value 3 and 4 gone. The next non-zero sample will be 5, and after that you will get zeros on both sides. This is the sequence. So basically there's nothing in between here. Okay, so the sample number 2 is retained, and where is the origin? The origin is here. Okay, this is the downsampled sequence. So this is the sequence that we have used to obtain the so this operation is the downsampling operation. Okay, so this is, if this is x of n, this is x of mn. The counterpart of this is the upsampling operation. If this is x of n, what you have with the upsampling operation by a factor of n, this is equal to x of n by n if n is equal to 0 plus minus n plus minus 2n and so on, 0 otherwise. So basically this one will insert n minus 1 zeros between two existing samples. Okay, so one is called upsampling, the other one is called downsampling, and you can utilize this these expressions in a systematic manner. So finally, what we are going to do is to look at an important step when both upsampling and downsampling are involved. Now, you may say, why would you do both upsampling and downsampling? If I want to change the sampling by a fractional rate, this is what will happen. So let us look at the following case. Y of n is equal to x of m by n times n. So that means there is upsampling and downsampling. So in time scaling, two operations are involved. If this is the case, the guideline is always do the upsampling first. Okay, upsampling first, followed by the downsampling. Okay, that's a useful order in which you can do, and again you can we can try out some examples where you can take this particular one and you can try some the change of sampling rate. Okay, so the homework or the task that I would leave with you, which I will discuss in the next session. So let me leave it as a homework task. I want to implement the following operation: x of minus m by n n minus n naught. Okay, so what are all the operations that are involved? There is a shift operation, n naught is the shift. So first we start by identifying that there is a shift operation. There is a shift operation. There is a upsampling operation because you have n by n. Upsampling is there. Okay, the third one is the downsampling. Okay, and then the fourth one is the time reversal. Time reversal. Now notice that this is the sequence that you can do. This is a valid sequence. So go through step by step and say how you will get y of n given x of n. What are the intermediate sequences that you will define in order for you to be able to do that? Again, very simple exercise in the sense that once you follow the steps in a systematic manner, you will be able to do it without any difficulty. But of course, we will discuss this in the next session. Now comes some interesting or important applications or of what we have just now studied. So, if you look, if I were to sketch this for you, say that I have x of n, I am going to upsample by a factor of 2. Okay, you will say very simple, I will take all samples, non-zero samples and insert 1 0 between every 2 samples. And then if I say that I am going to downsample by a factor of 2. Okay. Is the output sequence equal to x of n? Is the output sequence equal to x of n? Okay, check it. If x of n is given as 1, 2, 3, 4, 5, 6 with the origin at 3, the same sequence that we did in the last example. Upsample sequence, we'll call that as x prime of n. So, x prime of n, what will that be? It will be 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, dot, dot, dot. Okay, where is the origin? Sitting at 3. Okay, now go to the next step, downsample by a factor of 2. That means you are going to throw away one sample, every alternate sample is going to be thrown. So, let us call this output as y of n. Y of n will retain the sample number 3, throw away the next sample which is a 0, retain the next sample, throw away the next sample and retain the previous one, next one and so on. 6, on this side it will be 2, it will be 1, it will be 0, 0, 0. So, if I upsample by 2, I inserted 1 0 between every pair of samples. If I downsample by a factor of 2, I throw away one sample and what I actually ended up throwing away was the 0 valued samples. So, y of n is equal to x of n. Okay. Now, here comes the next question which is related to the application of this important principle. If I downsample by a factor of 2 first, and then upsample by a factor of 2, will my output y of n be equal to x of n? Input is x of n. Okay, very interesting question. Okay, I would like you to think about this and give me the answer next time. We will also discuss this in the class as a way of applying the important concepts that we have. All right. So, with this we have more or less covered all of the properties of sequences, operations on sequences and are able to now have a good handle on how to take these sequences and work with these sequences.